Let's talk about solving some basic first order differential equations. And all we have to do here is really just recall our antiderivatives from Calc 1, as well as some of our more robust integration strategies that we've gotten from Calc 2. So let's take a look at this first one. This first one, we won't need those robust integration strategies. We'll just need some basic integration strategies. So on this one, it says, find the general solution to this differential equation where the second derivative of x is equal to 15e to the 3x plus sine of 4x. Now, we just want the general solution, and we have a second order differential equation here. We have the second derivative. So what we're going to do is we're going to use our tools and techniques of integration. We're going to integrate both sides of this equation with respect to x in order to find the first derivative. So I'm actually going to write that on the next line so we can keep this guy here. So we're going to take the second derivative. We're going to take the integral of the second derivative because that will give us the first derivative. So y prime would be equal to the integral of the second derivative, which is the integral of 15e to the 3x plus the sine of 4x. And we're integrating with respect to x because we're trying to find this as a function of x. So the first derivative will become 15e to the 3x, just integration strategies. We do have a little constant multiple in that exponential function, in the exponent of that exponential function. So we'll divide by 3, plus again, another one of those it's like I think of it almost like a mini u substitution, but I'm not going to write u substitution. So then the integral of the sine of x is minus the cosine of 4x. And then we have to divide by the 4 to adjust for that 4x. And we will have a constant. Now, I know that this is going to be my first constant of integration because I'm going to actually have to integrate again. So I'm going to call it C1. And I'm going to go ahead and simplify that. So the first derivative is 5e to the 3x minus 1/4 cosine of 4x plus C1. Now we could just write C and then just when we get another constant denote it as something different, but I'm going to go ahead and use C1. So now we have the second derivative. We've integrated it. We found a general solution for the first derivative. Now we want to keep going. So we're going to do the same thing again. We're going to say, well, if I have the first derivative, the way I would find the function is by integrating the first derivative, finding the antiderivative, if we think of the language from the end of Calc 1. So we're going to be integrating 5e to the 3x minus 1/4 cosine of 4x. Now, in that first integration, we ended up with a constant, so I need to carry that down here. We're going to call it C1. And then I'm going to integrate each of those to find y of x. So y of x is actually equal to, we'll integrate e to the 3x again, so we get 5e to the 3x. We're going to divide by 3. We've got a minus 1/4. We're going to integrate the cosine, so that becomes the sine of 4x. And then we have to divide by 4 to account for that 4x. We've got C1, since that's a constant, it'll be C1 times x, and we will end up with another constant. We'll go ahead and call it C2. Now, there's not a whole lot to simplify here, but I will rewrite it because it'll be our final answer because we've now found the function. It's 5/3 e to the 3x. We end up with a minus 1/16 the sine of 4x. And we've got that C1x plus C2 where C1 and C2 are constants. And this is the general solution because we weren't given any data. We weren't told that the initial value of the function, we weren't told that, like, say, y of 0 was 3 or something of that nature that would allow us to find those constants. So we call this just the general solution. Now this is just our general solution to this differential equation. Now, if we had information, if we had more data, if we knew the value of the function at certain points, we could use that to find the specific function that would satisfy the given criteria. But in this case, that is our general solution. Let's look at another one. Let's look at finding the general solution to this differential equation. So we've got y prime of t equals t times the natural log of t plus 1. So in this case, we've got the first derivative and we want to find the function. So what we're going to do is we're going to say, okay, well, this is going to be a function of t that we're looking for, y of t. And to do that, we're going to want to integrate the derivative of y of t with respect to t. So we're going to want to integrate t times the natural log of t plus 1 with respect to t. I almost wrote with respect to x because I'm so used to it. My hand is used to dx instead of dt. So we want to integrate that function. So when we integrate that function, this is where we're going to utilize some of our integration techniques, because this is not just a basic integral. Like on the last one, we were just working with our basic functions. This is a product of two functions. And when we're trying to integrate a product, so kind of think in my little thought bubble up here, when we're integrating a product, what we want to do, I should have left my thought bubble a little bigger. When we're integrating a product, what we want to think about is maybe integration by parts. So going all the way back, it's nice here as we come to the end of the semester, it's nice to think about some of those integration techniques, right? To practice some of those integration techniques. So we're going to go ahead and use integration by parts on that piece. Now, I do not need integration by parts to integrate a constant. So I'm going to go ahead and just clean this up a little bit. The integral of 1 with respect to t is just t. But I would still need to integrate t times the natural log of t dt. I don't want that 1 to get lost in my integration by parts. So I'm going to go ahead and integrate it and write it over here. So far we have y of t equals t plus. Now I am going to end up with an integration constant when I integrate this. It's two terms, so technically we get two integration constants, but we add them together and they're still just a constant. So at the very end, I'll add my constant in. But here I want to use my integration by parts. So for integration by parts, what I'm going to do here is I look at t and natural log of t. If we remember, we had our little acronym for how do we pick our u and our dv. And our acronym said liate, or you could say ilate. And we pick our u to be the first function that occurs in this list as we descend, where L is for logarithmic functions, I is for inverse trig, A is for algebraic functions, T is for trig, and E is for exponential functions. So again, I could have added this into my little thought bubble over here. Just kind of my little recall integration by parts. So since I have a logarithmic function in my product, I'm going to go ahead and let that be my u, and my dv will be what's left. So my dv will be t dt. And so my du is 1 over t dt, and my v, when I integrate t, I get t squared over 2. So when I do my u times v and then minus v du for that integral, I can use my little notes right there. So t is going to be equal to the product of u times v, which is t, the integral of t, natural log of t, is going to be equal to, so this piece here is coming into this integral. Let me write my squiggly bracket like this. So we get our t squared over 2 times the natural log of t minus, and then my integral of v du. So when I integrate v du, I get t squared over 2 times 1 over t dt. Now I am going to simplify that, so let's bring it down another line. T before I integrate, t squared, t plus t squared over 2, natural log of t minus, this will become the integral of 1/2 t dt. Now this is y of t. Let's continue to carry that down as well. We're trying to find that function using our integration techniques. So now we can just integrate 1/2 the integral of t is going to become, let me carry everything else down so we'll have it all on one line. It's going to become minus, we're going to get t squared. We already had a 1/2. So when I integrate, I get 1/2 times t squared over 2, but I'm going to go ahead and just write that as 1/4 t squared. And then we, of course, have an integration constant. So we have plus c. And so that is my general solution. Because again, there's an integration constant there. So it's our general solution. Given more information, I keep saying that because on the next video, we're going to talk about if we had more information, more info, what we call initial values, like something like y of 0, if we knew that, actually we can't do y of 0 because the natural log is not defined at 0, but we could do like say y of 1, if we knew y of 1 equals 5. We can use that information to find the values, specific values of those integration constants, of those constants that are showing up in our general solution. So that's coming. That's going to come on the next video. But for now, we're looking for just the general solution. So this is our general solution to this differential equation. So if we were to take the derivative right there, we would find that the derivative would be equal to t times the natural log of t plus 1. So these are finding some general solutions to these differential equations. And just as a reminder, what we're doing here is really, let's go back to what I wrote here at the beginning. What we're doing here is we're really just working our antiderivatives. And now that we have integration strategies, we can find antiderivatives for a lot more functions than we could even at the end of Calculus 1.